Assalamu alaikum guys, welcome back. This is Shafat Khan on our screen. Okay guys, so in the previous lecture we talked about the variation in ionization energy as we go across a period. Now we are going to talk about, but there are actually a few exceptions to that general rule. Okay, generally as you go across the period from left to right, the ionization energy increases due to the several factors. You guys remember the factors? Radius, shielding effect, and nuclear charge and charge density. Okay, so as you go from left to right, what happens? The atomic radius shrinks, shielding effect remains constant, nuclear charge increases, charge density increases. As a result, electrons are more tightly held to the nucleus, more energy is needed to remove the outermost electron. Ionization energy as a result increases across the period. But to this general principle, there are a few exceptions that you must know, because these are frequently tested on the exams, especially on the past paper exams. So let's begin now. The first exception is from magnesium to aluminum. This is period 3, and in period 3 from sodium to magnesium there is a certain amount of ionization energy needed for magnesium and for sodium. Magnesium has a higher ionization energy as compared to sodium, following that general principle. But as you go from magnesium to aluminum, that principle is violated. Aluminum has a lower ionization energy as compared to magnesium, although according to the trend it is expected that aluminum should have a higher ionization energy. Okay, similarly the second exception is right above it, from beryllium to boron. Boron has a lower ionization energy as compared to beryllium, although expected is that it should have an ionization energy greater than beryllium. Similarly, the next exceptions are phosphorus and sulfur. From phosphorus to sulfur, sulfur has a lower ionization energy as compared to phosphorus. Phosphorus has a higher ionization energy against the trend, although sulfur is expected to, again according to the trend, to have a higher ionization energy, but it doesn't. And similar is the case, the last exception is right above it, from nitrogen to oxygen. Oxygen has a lower ionization energy as compared to nitrogen. Okay, again violating the trend. But guys, this doesn't mean that these are the only exceptions. These are actually the exceptions that are in our syllabus. Okay, so we are not going to go beyond these. We are not going to go look into the other periods beyond this. Okay, we are only going to confine ourselves to period 2 and period 3. Period 3 to be more important one. Okay, period 3 is actually the more important one because that's in our syllabus. Period 4 is no longer in our syllabus. It used to be in the syllabus quite a long time ago. It was removed. So of course you will find questions regarding period 4 as well, maybe in the A2 syllabus, so you'll need to skip those. Now let's talk in detail about this exception. Why does this change arise? Okay, so for the exception we'll need to first express both of them in their electronic configurations. I'm assuming that you guys know how to write it down in these electronic configurations, okay, in sp orbital format. Okay, I'm not going to go into the methodology of how you are going to write this down. Now magnesium has a proton number of 12. These are the electrons. Okay, 1s2, 2s2, 2p6, 3s2. If for aluminum the proton number is 13, meaning it will have 13 electrons. So the electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p1. Now if we look at the electronic configurations of both of them and compare them, the outermost electron of aluminum is in the 3p orbital, whereas the outermost electron of magnesium is in the 3s orbital. Which of the two have an electron that is better shielded, meaning which is on the outside of the shell, or which of the two have an electron that is more further away from the nucleus, or that is better shielded? It's aluminum, because aluminum has all of these electrons in front of it. The outermost electron, which is in the 3p orbital, has all of these electrons in front of it that provide the shielding effect, right? It is better shielded. Whereas if you look at this one, magnesium, only these electrons are responsible for the shielding effect. So that means aluminum outermost electron has a greater shielding as compared to the outermost electron which is present in the 3s orbital of magnesium. Okay, because the electrons present which are providing the shielding in case of magnesium are lesser as compared to those as compared to the electron present in aluminum. And remember guys, the shielding is always provided by the inner shell electrons, not the electrons in the same orbital. Okay, these two electrons are in the same orbital, right? And the inner shell the inner shell electrons are these ones. are these electrons over here, whereas in this case all of these are the inner shell electrons, or over here in this particular example these are in fact the electrons which are closer to the nucleus as compared to the last one. Or more simply, just remember that the outermost electron of aluminum is better shielded. Okay, it has a better shielding as compared to the outermost electron in magnesium. Therefore, it is less tightly attracted or less tightly held by the nucleus, less tightly held, and so lesser energy is needed, lesser energy needed to remove it. So lesser ionization energy. Okay, this explains why it does not follow the general trend, okay, from magnesium to aluminum. And the same reason applies to this difference as well, from beryllium to boron. If you write down the electronic configurations, you'll see that the electron of boron is better shielded as compared to beryllium. Okay, and remember I told you in the previous lectures that shielding effect, what the shielding effect does is it lowers the ionization energy. Shielding effect, it weakens the force of nuclear attraction that is keeping the outermost electron within the atom. Okay, shielding effect, it lowers the nuclear attraction. If it lowers the nuclear attraction, it has to lower the ionization energy as well, meaning the higher the shielding effect, the lower the ionization energy. Clear? This was the first exception, fully explained. And see, I told you, if you guys are able to understand one exception, then the other one will have the same reason. Okay, and there is the similar reason over here. So if the question comes, why is to describe and explain this exception, to explain this exception, or to identify the exception and explain why that exception exists. So this is the identification point from magnesium to aluminum. And why does that exist? Because the outermost electron of aluminum is in the 3p orbital and is better shielded. Therefore, it excuse me. Therefore, the outer electron of aluminum would be easily removed and will have a lower ionization energy. Okay, now phosphorus and sulfur. Let's talk about phosphorus and sulfur now. And why does sulfur has a lower ionization energy as compared to phosphorus? The reason over here is somewhat different, okay, and it's also a very high yield one because it has been asked frequently. Okay, what the examiner quite frequently asks you is to identify the exceptions, the first frequent question, and secondly explain the reasons. So we've done half the reasons, and let's do the other half. Now, if you look excuse me. Now, if you look at the outermost electrons of these two, 3p3 and 3p4, outermost electron of phosphorus is in the 3p orbital and outermost electron of sulfur is also in the 3p orbital. Now, there are 4 electrons in the p orbital of sulfur as compared to that of phosphorus. So, excuse me. Remember, the p orbital includes, or the p subshell includes 3 orbitals, px, py and pz. Now in these 3 orbitals, if you follow the Hund's rule, remember the Hund's rule? How does the Hund's rule apply? Hund's rule says that the electrons will always first fill in the orbitals which are empty and then will pair, right? Or you would say that the electrons will always fill singly first and then will pair up. So if you've got only 3 electrons, okay, I'll just erase this out. So according to Hund's rule, if these are the 3 electrons and you've got 3 orbitals in there, in this 3p orbital, 3p subshell, you've got 3 orbitals. The first electron will take, let's say, px orbital. The second will not come in the px according to Hund's rule. It will go and take the free positions. So there you go. And then the last electron will also take the free position. In this case, the first 3 electrons will take all the 3 orbitals. Now for the 4th electron there is no space left, so now pairing would occur, and so a pair of electron is formed. Okay. Okay, so due to this pair of electron, what happens? This pair of electron that has been produced, the electrons, they repel one another. Okay, and these are in fact the outermost electrons. Okay, because they are in the outermost subshell. If these electrons are already repelling one another, the repulsive force, what it actually does is it again weakens the nuclear attraction and it makes it easier to remove out the electron. Okay, now again it becomes easier to remove the electron, and if it becomes easier to remove the electron, then again ionization energy decreases. So now what are you gonna explain to the examiner if he asks you that why is there the exception, why does sulfur has a lower ionization energy as compared to phosphorus? This pair, this effect of pairing leading to reduced ionization energy is called spin pair repulsion or electron pair repulsion. Okay, or and this key term has the marks. You can use either of these two terms in your answers, but you must use them because these terms carry the marks. That's it. In the next video, we are going to talk about the successive ionization energies.